this microphone. Is it better? Can they hear?
Is it better? Can you hear me in Zoom? Okay, anyway, I will continue. So my goal today is to talk about the most recent things that were happening since the last co-stars. Also, this talk is some kind of extension of what you heard earlier today from Ansgar Reiners. I would like to begin by putting this presentation in the context of other invited talk by Semi Solanki that we heard earlier in the session. So what is the difference between magnetometry as we do it for the sun and stars? Well, we actually start with exactly the same baseline. We use the Zeeman effect for both sun and stars. So we learn from each other very much. The local calculations of Stokes parameters vector, for example, share the same principles. But then what happens is that for the sun, of course, we have spatially resolved observations. So any horizontal information we get directly from images. But for the stars, we always have unresolved observations. And this difference then results in a very different next steps of the analysis. For the sun, the relevant information that remains to be recovered from observations is vertical information, how much velocity field, temperature, magnetic field changes with height, whereas for the stars, it is horizontal information that we are caring about. And then when it comes to comparison, it's not entirely obvious, can we compare with the solar and stellar results. But let me start by reminding you about two principal methods of direct measurements of magnetic fields on stars, and I'm aware of radio, but I said on stars, not near stars. So it is still Zeeman effect. And one method is Zeeman broadening, that is how much spectral lines are broadened by the field. So here you see illustration of how this effect changes the line profile shapes of two representative lines with slightly different Zeeman splitting patterns and effective lambda factors. And you can see the result is actually quite, this results in quite small changes for the fields under 1 kilogauss. You can also notice that besides the broadening, lines also become stronger. And this realization that intensification provides information about the magnetic field is relatively new. Well, it has been suggested a long time ago by Bieber also, but large-scale application of this method is relatively new. So with this method, we are sensitive to total magnetic field strength. It has been called different words, total magnetic flux, small scale field, but let's say total field. It requires strong fields to be visible. It requires normal high-resolution spectroscopy, which is an advantage because we have lots and lots of observations suitable for this type of measurements. It gives no information about magnetic field geometry, which is a curse and a blessing because we can also say it is independent of magnetic field geometry. So it provides unbiased field strength estimate independently of how complex the magnetic field on the stellar surface is. But what we care about when applying this method, okay, if the field strength is increasing, we get stronger and stronger magnetic fields, but these values are perhaps not very representative for cool stars we are talking about here. But what we care about when applying this method to other stars is that, especially in the near-infrared wavelength regions, the splitting is sufficient to change the profile shape. So it's not just the small broadening that we see, but we see impact on the profile shapes. And it turns out that we need to account for the distribution, not of the field geometry, but of the field strength over the stellar surface. So you can see examples here, how 2 kilogauss field, which is quite typical for active M dwarfs, for example, can give very different distortions in the profile shapes of Zeeman sensitive lines, depending on whether or not we take just entire star covered by 2 kilogauss field, or split it 50-50 for kilogauss 0, or assume some kind of distribution of the field strength. So it is a large effect. It needs to be taken into account in the modeling of Stokes size spectrum. And a typical methodology which is applied here is the squares fitting, the normal procedure, and the kind of technical requirement is to have polarized radiative transfer code. Unfortunately, there are no simple methods of modeling this, no simplified tools. We need to do full radiative transfer in the magnetized atmosphere. A couple of results of this methodology applied to solid type stars. We have demonstrated a few years ago that magnetic intensification, even in the optical lines, give access to total field strength of active solid type stars. So, for example, here illustration of application of this technique to everyone favorites EK Draconis. You see comparison between best fit red spectrum. This is spectrum with magnetic field, and observations for 4 lines from the same multiplet but different Zeeman splitting pattern. The top left one is magnetically insensitive, and you can see that the difference between magnetic and non-magnetic spectra, the dashed and solid line, is actually huge. So it's not a minor effect we're talking about, and that allows to derive magnetic field of 1.4 kilogauss in this particular case. There is a nice correlation between this total magnetic field strength measured for sun-like stars and Rossby number. There is also correlation between the filling factor. The stars with stronger field indicate larger fraction of the surface covered by these fields. What we are uncovering now with a bit more observations and pushing our observations in the infrared, that there might be a sort of chromaticity of these mean field strength measurements. So this is the comparison of the measurements of essentially the same group of stars in the optical versus in the infrared, in the H band, and H band shows factor of 2 to 3 weaker magnetic fields. So we don't currently know how to interpret these results. Perhaps we're seeing height dependence. Perhaps we're seeing sensitivity of different sensitivity of optical and near infrared to temperature structure, maybe of magnetic and non-magnetic regions. But there is more to this picture than just a single average magnetic field strength. Now, it is possible to push this methodology a bit further and try to reconstruct map of magnetic field, not a vector field, but of the field modulus. So this, we sort of demonstrated possibility of this using famous LQ Hydra, young sun-like star. And we see the two maps. This is the temperature. This is magnetic field modulus. So a very different type of magnetic field map compared to ZDI. And it's really boring. It only shows a little bit stronger fields at the poles, maybe not surprising. But overall, there is no structure to it, meaning that the field that is reconstructed with this methodology, the small-scale field, is not clustered in large-scale features on the stellar surface. It doesn't form large spots. And we happen to have Stokes V from the same observational data set, and this is how classical ZDI would look like if we apply to the same data set, ZDI version. And you can see a huge difference here, less than kilogauss average field strength, 2 kilogauss here. So this tells you how much ZDI is actually missing the magnetic field flux. You have already seen this picture earlier in the morning. So there has been a series of applications of measurements of mean magnetic field to M dwarfs enabled by the new generation of near infrared spectrographs like Carmenes, Spiro, and so on. The largest database of measurements was provided by Ansgar Reiners. So this is some random example from their work. But what I would like to emphasize here, that again, the difference between magnetic and non-magnetic calculations is not so small. You can see this dotted line is the non-magnetic spectrum. In the near infrared, you start seeing splitting of lines, and we're also at the stage when we can pretty reliably model Zeeman effect in molecular lines, which is also a recent achievement. Again, emphasizing that it's not just the Zeeman broadening that gives information about magnetic field, it is also Zeeman intensification, which in fact opens possibilities of measuring magnetic fields on rapid rotators. You can see one example here, famous eclipsing binary YY-GEM. And again, it is pretty straightforward to see the difference between magnetic and non-magnetic calculation. So these measurements using intensification has been carried out now up to VSI of 70. So analyzing Stokes I is not limited to small rotators. That's the message here. What is the overall statistical distribution of this total field strength measurements from Stokes I? You have seen these pictures earlier today, so there is a usual relation between field strength and Rossby numbers indicating unsaturated and saturated regimes, and there is a tighter relation if you switch to the magnetic flux to rotation period. There seems to be this effect of magnetic field in the saturated branch being limited by the kinetic energy available from convection. But here, what I'd like to emphasize, what I'd like to discuss briefly, is the scatter of objects in the saturated regime. We don't really know what this is due to, and there are different hypotheses. Maybe we are catching stars in different phases of their activity cycles, or maybe this is due to some age or evolution effect. There has been a recent study that possibly provided an answer to this question, and this was done by a team working with apogee data, who applied this methodology of measuring magnetic fields from Stokes I to M dwarfs and Pleiades, so sample of objects evolving in the same environment, and they got much tighter relation between magnetic flux and rotation period. So it seems that this scatter that we see in such diagrams here is due to evolutionary effects possibly. Now let's turn our attention to the second direct measurement method, namely deriving global magnetic fields from spectropolarimetry. So this is the same two lines for different line of sight magnetic field. So in the Wick field limit, the Stokes V signal, local Stokes V signal, is proportional to the line of sight component of the field and to the derivative of Stokes I, because its line of sight component can be positive or negative, meaning that we have this cancellation problem that everyone is talking about. When we increase the magnetic field strength, eventually we go away from this proportionality to the derivative of Stokes I. So the structure of the line profiles become more complex. And also one thing that is appearing, the amplitudes of the signals are no longer tracked by the ratio of effective lambda factors. So that's the prominent effect coming from deviation from the Wick field limit. This type of modeling is actually easier to do than modeling of Stokes I, because Stokes V is the first order effect. It is much more similar between different lines, and therefore in typical ZDI works, people successfully apply simplified line formation techniques, not doing full radiative transfer, but applying analytical formulas, or even taking Gaussian as local profile and derivative of a Gaussian as the local Stokes V profile, and that gives pretty robust results for many stars, especially in Wick fields. This methodology is sensitive to field geometry. It does require, however, specialized equipment that is not available universally at high resolution spectrographs. We need to do high resolution spectropolarimetry. You have heard many times about ZDI. I've seen some movies. Here is a couple of movies that I would like to play. So just a message that if we have a magnetic spot and we have a time series of Stokes observations, we can both track position of that spot on the surface of the star and distinguish orientations of the field, distinguish azimuthal from radial, for example. I show these two movies to illustrate that even in the case of slow rotator, so in this case, this sin I is smaller than the line width, we still have very significant rotational modulation due to simply changing of the aspect angle at which the surface structure is seen by us. So D in ZDI is actually unnecessary sometimes. Of course, in this picture, we're still losing a lot of surface resolution. A series of papers was done by Travis on based on recent observations of sun-like stars, and the kind of step forward that was achieved in the last few years is the ability to measure really weak fields. That was achieved with arguably the best spectropolarimeter in existence, but the least used spectropolarimeter because somehow our community has very limited access to it with PEPS spectropolarimeter at LBT. Here is an example of several detections of magnetic fields on weakly active, even inactive stars. Here is, for example, where is it? Tau Ceti, and you can see the line of sight magnetic fields that the numbers force us to change from Gauss to milligauss. And for at least one of the star, we also did reconstruction of the global magnetic topology. You can see it's 51 Pec, the famous exoplanet host star with a global field of a few Gauss. Of course, again, this is global field, the largest scale, and as was mentioned many times by Sami, there is much stronger local field in this star. And what we're seeing is the result of constellation. Now, magnetic fields in M dwarfs have been studied a lot thanks to recent surveys with Spiro mainly. And here is a kind of almost random selection of results because there is so many exciting results coming from this work. Proxima Cen has had its magnetic field mapped. I would say somewhat surprisingly strong magnetic field, several hundred Gauss global field. We have seen evidence of very stable magnetic fields in slowly rotating M dwarfs, for example, for this object in 3 different years, it doesn't change its global field also having quite simple geometry. On the other hand, we also have seen changes in the magnetic field. So here it seems to be a flip of the polarity of the field. So at the moment, it's very difficult to say, to make general conclusions such as what is the typical length of magnetic cycle and how it shows up in the observations. This is the usual attempt to summarize this type of results in confusogram. So I would like to discuss here only the sizes of the symbols, which are proportional to the field strength. This is plotted as a function of mass and rotation period. The puzzling aspect is this coexistence of fields of very different strength in the same mass and rotation period. We still don't have explanation for why this is happening. And then finally, again, I was talking about 2 types of magnetic field measurement, small scale fields or total fields, and the large scale fields. These are 2 different things, please. Remember that the ratio of them is here plotted as a function of mass and as a function of total field. So there is some pattern in this figure. The largest ratios are observed in stars with lowest mass, early M dwarfs, except they unique typically show more than factor of 10 difference in field strength. So to kind of conclude, what we seem to be seeing is that at small scales, we have very complex structure. We have global structure that is sometimes quite simple for M dwarfs. So the sum is something like that, probably. which looks rather similar to some of the emission simulations coming out of theoretical books. And I'm leaving here the conclusions and challenges to have some time for questions.
A couple of very quick questions, so we can move on. Questions somewhere? Oh, yeah, over there in the back.
Shouts.
There's just shouts.
Your second question, what needs to happen for us to detect it around works?
Very good question. The question is how to detect magnetic fields in round wolves. Probably your neighbor Ansgar is the one to ask, but try harder. No, okay, seriously, this has almost been done. So there is this object LSR 1835 that everyone studies. Some people call it brown wolf, some people say it's not yet brown wolf, but it's on the border with the spectral properties very similar to brown wolf, and magnetic field has been detected in it. So go to 10 meter plus telescope, do low resolution spectropolarimetry. That's what I would say. Maybe what we're trying now with virus is to use iron hydride molecular lines and try to detect small scale field. But with polarimetry, I think you need to go to large telescope.
Okay, thanks a lot. This is working, right? Okay, great.